Hello, let's look at another problem with the topic of moment. Specifically, this problem talks about force-coupled systems. That's what they're discussing, force-coupled system. A blade held in a brace is used to tighten a screw at A. A very confusing way of saying this is a handheld screwdriver. I don't know if you've seen any of these. You typically put your chest at point C and kind of push a little bit, or you hold it with your hand at point C, and then by rotating handle at B, this is how you tighten or loosen a screw. So anyway, there are forces at B and C that the components are given. B is only in K direction, in Z direction. C has I, J, and K. It gives you the equivalent moment and equivalent force at point A. Equivalent means replace all of these. So I get rid of all of that. Instead, I put a reaction at A. Sometimes we show it as F sub R. In this problem, it uses notation of R, which is summation of all existing forces in vector form. So if you add B, all of these components of C in vector form, that's what this equivalent force is. So they get rid of all the forces, put one equivalent force at A. Also, because these create moments about various points, including A, you have to put add all of the existing free couples moment plus summation of all R cross F's. In this case, we have 1, 2, 3, 4 forces. This C is just components of same force, but we'll treat it as 1, 2, 3, 4 forces. So you have 4 R cross F's that you have to add together. There is no couples moment. So that one is 0. So the problem gives us, you can see the notation is a little bit different. That means just about point A. This tells you is 13.5 I units of Newton meters. This one tells you minus 25 I plus Ryj plus Rzk units of newtons. So these are the information given. Part A says, hey, find B, Cx, Cy, Cz. Find these. This is part A. Part B says find these two. And part C asks what's the orientation of the slot or that blade or screwdriver. We will talk about that. So here's a little bit larger if you want to pause the video and read it and make sure you fully understand it and write your notes and all of that. So while you do that, I'm going to quickly write it again here. Fr, or in this case R, minus 25 I Ryj Rzk, and Mr about A. Again, just a slightly different notation, means the same thing. 13.5 I Newton meters. So let's just start with finding B, C, and all the C's. This here is summation of all these forces. So why don't we just add all these forces together? All of the forces, all of the components in I got to be added together. Cx, I. There's no other I component. That's the only I. I don't know why I put parentheses around it, but doesn't matter. The only one in J direction is Cyj. In K direction, I have Cz and I have minus B. It gives me minus B. I'm going to use just minus B as well. And K. So this is equivalent to 25I Ryj and then Rzk. This is what's given. So by just looking at it quickly, there's one that I don't even have to do any equations or anything. I can quickly get that Cx is minus 25 newtons. That one is done right away. The second one I'm going to look at is the J components. Ry or Cy is the same as Ry. Doesn't help me. Two unknowns. I can't figure it out yet. So I got to do more work and come back to it. And then lastly, I'm going to do a wiggly squiggly line here. These two are same. So Cz minus B equal Rz. Way too many unknowns. I can't touch these yet. So this is all I can do with this R for now. But I have another equation, right? I have another sets of calculations that I can do. So let's go do MR and then see what we can find out. So just let's have these here for now. Let's work on our moment. All right. The moment, as I said, it's a summation of, I apologize for rewriting and writing these over and over. Summation of all R cross F's that you see here. In other words, you need to have an R position vector cross B, another position vector R cross C, the full force C, or you can have it individual components. Position vector always is from the point to the line of action of force. So in this, the first case, it goes from point A to line of action of B, which is point B. For the second one, it goes from point A to line of action of C, which if I take point C, all of these forces, the line of action crosses from point C. So I'm just going to take it as AC. Okay. I'm not going to draw the table coordinates, calculate the position vectors. I've done plenty of videos on it. So please, you can go back, watch the position vector video or other examples that I fully calculate how to do a position vector of calculation. So in this case, I'm just quickly going to write down and skip a little bit of math here. The I for A to B is going to be 240, and I'm converting it to meters right away. 180 in J and 0 in K. Force B, all I know is minus B in K and 0 and 0. This is meters. B is newtons. You don't have to put it there yet. I don't know it. The next one I'm going to do is R from A to C. It's just a straight line. 240 plus 240 is 480. 0, 0. And then I have Cx. Did I calculate Cx? Yes, I did. Minus 25. Minus 25. This one I know it's newtons. Cy and Cz. So these all have to be minus 13.5 I Newton meters. This is what the problem gives us. So let's do the math here. So quickly we do I 180 plus minus B minus J 40 minus B. Do the second one is going to be minus J 480. If you are confused about how I do this, please go back and watch the lecture on cross product and how you do a cross product and how you do the calculation of the cross product. Oh, I forgot to write K here. Okay. This is my I, J, and K. So I know I only have I, the rest should be 0. So let's see. This is going to be minus 13.5. So 180 minus B equals 13.5 Newton meters. This one is meters. So therefore my B is minus 13.5 Newton meters divided by 180 millimeters. These two cancel each other out. All I'm left with is 75 newtons. So I found my B. I had Cx before. I have B. I still have 2 more. So let's do the K because it's 0. There's no K in my final answer, so this should be 0. So 480 meters Cy equals 0. So that means Cy is 0. Find that one too. And then this whole thing here should be 0 as well. So 2 minuses, so it's minus 240 minus B, which I already found is 75. 480 CZ. This whole thing got to be 0. B is 75. If you do the math on this one, your CZ should turn out to be 37.5 newtons. So I found all of these 3. If you remember, I had left some stuff back here. Oh, sorry, right here. CZ or CY, I figured is 0. So that means my RY is 0. And then my CZ turned out to be 37.5. My B turned out to be 75. So let's write these a little bit more clean. So B was minus 75 K newtons. And C, I could just write it as one vector. Minus 25I plus 37.5 K. Cy was 0. Okay, this is also newtons. From slide 1, I had Cy equal Ry equals 0. I had minus B plus CZ equal RZ. So minus 75 plus 37.5 newtons equals minus 37.5 newtons, and that's my RZ. So I think I've fully solved part A and part B. Last part of the problem, I gotta kind of read it again. What is the orientation of the slot in the head of the screw? Or I think it means orientation of this. Oh, orientation of a slot in the head of the screw for which the blade or the screwdriver is least likely to slip when the brace is in this position shown. So we don't want this. So in other words, what is the best position for it that this screwdriver doesn't just slip out, fall out? Okay. So let's look quickly at my R, the force I put on there. Let's write it as a vector form. Is minus 25I minus 37.5 K Newton. This is my equivalent force that is in that direction. So it has a component in, let me draw it here quick. It has a component in negative x. So let me switch colors a little bit. There we go. The x component of it is minus 25. And then it has a minus 37.5 in negative k direction. A little bit larger than that. So minus 37.5. And there is no j component. So all of these forces, the cy, cz, ck, cx, cy, cz, and b, will result in a force that's kind of like that. This is my r, okay? So if my screwdriver, trying to draw the screwdriver, and the slot in the bolt or the screw is this way, the 25 is trying to push it into the screw, so that's actually helping me. And then the negative 33 and 7 is trying to push it this way. So it's going to slip out. So that's not a very good spot for it. Because the problem said, what's the best spot so this doesn't slip out? On the other hand, if my screw is vertical, is in the vertical position, so the slot is like that, and my screwdriver is kind of like this, I think that's a good spot for it, because the 25, again, is trying to push it in, which is good, and 37 is trying to push it out, but it's not going to move. So I would say an answer to this would be vertical position of the slot in a screw or screw head is the best to avoid the blade or screwdriver slipping out. It just wants you to think about it a little bit. The wording really doesn't matter. Wants you to think about, okay, what does these forces mean for us and what we do. All right, well, thank you very much.